It's my pleasure to talk to you tonight about SPHEREx. Great turnout here. So SPHEREx is a recently launched satellite, launched 13 days ago. And it's a type of satellite called an explorer satellite, which means that it's competed. You propose, multiple people propose their concepts, and NASA picks a couple, has a competition, and then picks the winner. So we were selected for implementation in 2019. These are not expensive missions. They're cost caps, so every decision we make has to be weighed against science versus dollars. So we're very used to that. And selection in 2019, launch in 2025, that's super fast for a space mission. Okay, so SPHEREx has a new capability, which is to map the entire sky in 102 colors in the near infrared. Hasn't been done before. And with that new capability, we can address some really exciting fundamental questions in astrophysics, including how did the universe begin, how did galaxies begin and evolve, and what's the origin of water in the galaxy, while creating this unique all-sky multicolor survey, the first of its kind. Okay, so I'm going to talk a little bit about the design, whip through the science, and then show the launch, which is the really cool stuff. Okay, so here we are. This is a simulated video of SPHEREx. You can see we're in low Earth orbit, and we have this unique cone design. As we go by here, there's the solar panels. So we always have the solar panels facing towards the sun. And SPHEREx goes around the Earth pole to pole, North Pole to South Pole, along the sunrise-sunset line that you can see there. That's called the terminator. So we're in a terminator orbit, and that always keeps the sun 90 degrees off one side and the glowing infrared Earth below us. Now, we're in the infrared, so we see thermal emission, and that means that the telescope and the detectors have to be pretty darn cold. And we do that with those unique cones and basically radiating heat out to the cold of space. And so that cools the telescope to a very low temperature, below 80 degrees above absolute zero, and the detectors below 50 degrees above absolute zero. As we peel off the solar panels, they magically disappeared here. You can see it's a small telescope, about that big, 20 centimeter effective aperture, 3 mirrors, but don't let the small size fool you. It's got an enormous field of view, like 40 square degrees on the sky, so it's collecting a ton of photons in spite of its small size. The detectors are top and bottom here, and we take images basically by pointing the telescope. And the way we get all these colors is there's a filter that goes over the detectors where the bands move over the detectors. Very simple design. We just point at the sky for about 2 minutes and we get an image, and then we keep moving to get all the colors. To do that, we have to have a very agile spacecraft. So the spacecraft is provided by our partners, British Aerospace, in Boulder, Colorado. Okay, so here's sped up video of how we do our observations. Now, we always have to have the sun 90 degrees off axis, and we can't look too far down towards the Earth, or thermal emission from the Earth will get into the telescope. So that means that we can point within this half circle at any given time. And we love the Earth, but the Earth keeps getting in the way. So as we're going around the Earth is coming up and shining in. So at some point, we have to do a big slew so that we don't get the Earth shine into the instrument. And so each of those exposures there is about 2 minutes, and you can see we're getting a few of the colors after a few observations. But to get the full picture, we have to do this over the whole orbit multiple times. Okay. And then really sped up, here's how the orbit looks like, the observations look like over the course of a year. So the sunrise-sunset line is always obviously perpendicular to the sun, and as the Earth goes around the sun, the orbit follows the sunrise-sunset line, so that circle that we're observing in rotates. And after 6 months, it will close. So basically, we get a full all-sky survey in about 6 months. And over our 2-year prime mission, we get 4 of these all-sky surveys. So that was greatly sped up. That was 6 months that went whipping by. Okay, briefly, let's talk about our core science questions. Where's the water in our galaxy? How did galaxies begin? How did the universe begin? 1 slide each. Okay, so first question is, where's the water in our galaxy? So you might think it's in liquid, but you would be wrong, or vapor. It's actually in the form, most of the water in our galaxy is actually in the form of ice. And so that ice forms on the mantles of dust grains through very slow interstellar chemistry. And it's really important for those of us on Earth because it's thought that the oceans, the water in Earth's oceans, came from these interstellar icy reservoirs originally. That's where the water originally formed. And so we want to know how abundant this water is. And it's very important in the early stages of star and planet formation because that icy dust is what forms into the planetary disk where planets come from. So what we're doing with SPHEREx is we're looking at a background star, and we can see the characteristic fingerprints of ices that are on the dust grains. So this spectrum, you can see a very deep dip here from water, but it's not just water. We also see features from organic ices as well. And these are not well studied. The astronomy community has maybe a couple hundred of these spectra. So what SPHEREx is going to do is map the entire sky this way, and so we'll have millions upon millions of measurements of the abundance of water and these other kinds of organic ices in the early stages of star formation, going from the original dense molecular clouds where stars are born through the early stages as stars turn on and form their planetary disks. Okay, then our next question. How do galaxies begin and evolve? So this is a cartoon that shows the history of the observable universe, going from the Big Bang on the left to today on the right. And several hundred million years after the Big Bang, the first galaxies formed out of the primordial material from the hydrogen and helium that were there from the Big Bang. And so those galaxies first turned on, they ionized the gas around them. And then the whole history of galaxy formation is those initial galaxies formed, star formation, and galaxies increased and increased and increased. And it actually peaked about 5 billion years after the Big Bang, and it's been on a slow decline ever since. So with SPHEREx, we have a small telescope. We're not going to go back and see extremely faint galaxies on the edge of the universe like JWST. We can do something very unique, and that is to study the total glow emitted by all these galaxies. It's called the extragalactic background light, and it's just basically the total emission from all galaxies over cosmic history. And so that background is a treasure trove because it contains all that history, including this first period when galaxies first turned on through all of cosmic time. And we use the fact that galaxies aren't just random, they cluster together in a predictable way. We can use that pattern to measure basically the aggregate emission from galaxies. And then with spectroscopy, we want to invert this history so we can understand the emission in cosmic time, how that happened. Okay, last theme, how did the universe begin? And here, we're particularly interested in this very early moment at the Big Bang. And so when the Big Bang theory was invented, about 100 years ago, there's been a modification to it about 40 years ago, which is the idea that in the first moments, the universe went through this period of rapid expansion called inflation. And that solves some really puzzling problems with the original model, like why is the universe so uniform? Why is it so flat? Well, inflation solves those problems, but it creates others, like how did that happen? And inflation, this expansion requires some exotic state of matter energy. And so since it was invented in the 80s, people like me, experimental cosmologists, have been trying to understand more about it, show that it happened. And every measurement we've made to date is consistent with this picture, but we still don't know what the mechanism was, what the exotic physics was that caused inflation. So we're going to use the universe as a laboratory here with SPHEREx. And basically the idea is, at the time of inflation, the observable universe was smaller than an atom. And tiny fluctuations, quantum fluctuations at that time, were expanded by inflation to enormous scales. And those signatures are on the sky today. And the interesting thing is, those fluctuations created the hot and cold spots in the microwave background, and they created the overdense and underdense regions that are traced out by galaxies. So what we're going to do is SPHEREx is going to make an enormous three-dimensional map of galaxies, getting their distances from redshifts and positions. So that three-dimensional map traces out these structures, and these structures on large scales were set up by the Big Bang itself. And so with this map, we hope to understand more about the exotic physics of inflation. Okay, and while we're doing this, we're going to make this unique all-sky data product, first of its kind, put that data out to the community and let the community have lots of fun with it. And with a new capability like this, you often have new discoveries, and so we want to expedite that process by getting the data out and letting the community find what they can in it. And there's a long history of missions like this being very successful and being used by the astronomy community for years and years and years, including the IRAS mission, which was the first all-sky survey in the infrared in the 80s from Caltech, still in use today by astronomers. Okay, so with that whirlwind tour, I want to say a few things about our launch. So in January here, this is the satellite in that box arriving at the Astrotech facility at Vandenberg. It's just gone on a cross-country road trip from Boulder, Colorado, where it was assembled, to the west coast of California here. About the time that arrived, this is a picture of our booster landing from a previous mission. And so these boosters are used again and again. This is a SpaceX Falcon 9, and that's the way the business works these days. Just fly it again. So that is the booster that we actually flew. Here's the spacecraft at the integration facility at Vandenberg. So you can see it all assembled. There's the solar panels. So this is basically where our team left off. We had finished assembling and checking out the spacecraft, and then the next step is to assemble it with SpaceX onto the vehicle. So here's that process starting. Here's SPHEREx being lifted onto the next stage of assembly. Okay, and then this is the view of the assembled spacecraft inside the fairing of the rocket. So actually we had a co-launch with another satellite called Punch. Actually there are 4 satellites. So at the bottom there's the adapter ring that goes to the vehicle. There's another ring here that's where you can see 3 of the 4 Punch spacecraft. They look like boxes on some of those ports. And then we're up there with another adapter ring. That's us on top. And you can see the cones. And then the outside of that is the fairing. You can't really see it from this picture, but this fairing is enormous, and we could probably fit about 2 of these things inside the full fairing. Really incredible. This little video shows the fairings going together. So this is called encapsulation, where the assembled payload's integrated with the fairing. Okay, so we did that twice because there was a problem, but got it right. You might, if you're following SPHEREx, you might have noticed that our launch was somewhat delayed. So it was supposed to be the 27th of February. And so this is a little exercise from some graduate students at Caltech trying to figure out from all the launch slips when we would actually fly. And the red line is the most recent prediction here. I've seen this whiteboard and there's more lines now, but on the March 3rd, they estimated the launch at March 10th, which is when we tried to fly, except weather stopped us. So they were right on the money. Meanwhile, we had to find diversions in beautiful Lompoc, which is actually really beautiful. So that involved great wine tasting, investigating the beach and railroad station, outdoor mural gallery, and skydiving that some of the postdocs did. Okay, so this is launch day. So you can see the assembled rocket with the payload. Remember how enormous that payload was. So this whole thing is pretty big. This is a group picture, mostly with SPHEREx. Everyone you see with a red shirt on here is from SPHEREx. Blue are punch people. People who aren't wearing shirts are either from NASA or from SpaceX. So that gives you some idea of the team involved. This is actually taken on the landing pad where the booster comes back down. And that's our vehicle back there. Okay, but because we're a small project, every project like us needs superheroes. And people don't have duplicate jobs, so pretty much everyone needs to be a superhero. These are some of the superest superheroes. So these were people at Caltech who tested the instrument. Again, cost cap mission, so we did a lot of the characterization of the instrument actually at Caltech, not at JPL.
3, 2,
and here's the launch.
Ignition. Liftoff of the Falcon 9. Go SpaceX, go SPHEREx, go Punch.
SPHEREx and Punch on their way to map out our
nominal.
universe like never before and revolutionize
Vehicle
space
pitching
weather
downrange.
forecasting.
Stage separation confirmed.
And back ignition.
Stage 1 boost back startup.
Coming up next, we will see fairing deploy, and that's when the two fairing halves will separate and expose SPHEREx and Punch to the atmosphere of space.
Fairing separation confirmed.
In about 30 seconds, we will have payload deploy of SPHEREx.
SPHEREx separation confirmed.
SPHEREx is drifting away from Falcon 9's second stage, confirming deployment. The mission isn't over yet. Falcon 9's second stage is still carrying NASA's Punch mission.
Separation confirmed.
Wow, look at that. To actually see them, that's great.
Okay, so that was the launch. Thank you. So a funny thing happened on the way to low Earth orbit. Yeah, so you saw that separation, right? And we had worried about whether it was going to be tipped off or off nominal. You know, would it be 2 sigma off nominal, 6 sigma off nominal? What would we do in all those cases? The thing we hadn't anticipated is the separation was perfect, okay? And so what that meant is that the spacecraft was actually in the shadow of the vehicle for 3.5 minutes. And meanwhile, the spacecraft's trying to find the sun, and it's in the shadow. So it was rather confused there for a few minutes, but it did figure it out once we got out of the shadow of the spacecraft. Then the other thing is we had some communication problems on the ground. So we missed our pass over Antarctica, and then when we came halfway around the Earth to the Arctic Circle, the Svalbard station, the station there dropped communication for 3 minutes. And so the last video I'm going to show you is the science team trying to figure out what's going on, as we haven't seen anything from the spacecraft.
If we don't get FAIRBANKS, we have to go back to Antarctica and fix the problem. Yeah, I know we thought, yeah. Well, I've heard this. Data! Yeah, there was a bit of a delay for us on the control center because we didn't have any of that audio while we were listening. I had it on my computer, but I was looking at other things. Anyways, we did get communications, and at this point, SPHEREx
in its desired orbit. The spacecraft is happy. We're turning stuff on. We fired off the lid. So things are looking, instruments cooling down quite well. And so we're looking good so far. And with that, I'll say thank you very much for listening and happy to take questions.